All right, welcome back everyone for our next lecture in our Math 20C, our multivariable calculus, getting started today with our introduction to vectors, okay? And so I'm going to jump right in and start to share my screen. And for students that have taken force vector, right, which direction, how big of a force is acting upon a particular particle or an object, right? You've probably seen that even like the velocity vectors, which how quickly a particle, an object is moving in the vertical or horizontal directions. We might have seen those before, but in case you haven't, we'll do our introduction to some vectors and notation in this discussion today, okay? So in our text, section 12.2, we're going to be looking at vectors, okay? So starting off, a scalar, before we get into vectors, right? A scalar is kind of a numerical value, right? A numerical measure, right? That identifies a constant amount, right? Value, result, but doesn't really have any other features to it, right? We can identify how far we need to walk. I'm going to measure the length of my desk is 3 feet across, right? That 3 feet, scalar value, how much that quantity is, okay? How much something weighs, right? The mass of an object, those are all scalars. These values, these measures that are associated, tied to a particular object, item, idea, okay? But are simply just the kind of numbers, constants, really. So then when we get into a vector, when we start to introduce that, is an object that has both size, or we'll start to call it magnitude, right? Length, and direction. And again, for those students that might maybe have taken linear algebra, I'm sure you've talked about vectors in that course as well, right? But this vector, this idea, has these two quantities, these two qualities, characteristics associated to it. Size, right? A magnitude, how big that vector is. So I can get into that force. How big of a force, which might be some scalar quantity, right? But also with that size, that magnitude, that value, comes a direction. Which direction is that force pushing? How quickly is that object flying upwards? So on. So there's a direction to these vectors, okay? And so a kind of note here is that a vector does not have a particular location in space defined for the vector. Really all we have is the size and direction that is pointing, right? Because we typically draw these arrows, but really it can live anywhere in space, anywhere in our 2 or 3 dimensional coordinate systems, okay? And so getting into some images, some ideas here, right? We might have this vector going through these 2 points, right? So let's say here, P1, P2, these 2 points. And we have this vector, okay, it's going to start at that point P1, and we're going to the direction pointing towards P2, right? That distance between those 2 points is going to be our magnitude, the length, the size of that vector. the direction, kind of like that slope we start to get into, right? Kind of what angle are we moving at? Pardon me for being kind of big here on the screen, right? That's going to give us our direction. So we can overlay our coordinate system to kind of imagine, okay, where this would be in space. But truly, this vector could be, and we can shift it around. Taking that particular vector, the size isn't going to change, even if I just shift my paper over. The direction, as long as I maintain kind of that angle, if you will, that slope, that's not going to change. I can slide it all around my paper, and we'll still have that same vector. It's just how we're orienting our points and so on that may change. But that vector is going to be consistent. The size, the length, the magnitude, and its direction that it's pointing can be anywhere and still be that same vector. All right. And so in terms of our notation, what we can do, we could label those 2 points, right? Our starting point we can call kind of our initial point, where that vector is originating from, or it'll be the tail of our vector. And here's our terminal point, right, where that vector is ending. And we go in that order, where my vector is starting at P1, ending at P2. And for this vector notation, what we can do, we'll use this little arrow. I'll do a little half arrow. You can do a double-sided arrow. As well. Right, you'll see that notation. So this is that vector. Here's our notation for representing, writing that vector. Or if we give it a name, we can call it this vector A, like so. Okay, or with the double like so. The textbook might use a bold, okay, bold typeface, and just have the letter A, right? But for my work here, I'm gonna put a little arrow over the top to let us know that we're talking about a vector, that it has a size and a direction. If it's just a scalar or constant, you won't have those values and you can identify those quantities, okay? And so for any vector, we'll have that size, that direction, okay? And that can live anywhere in space, all right? And so here, 2 vectors are equal if the vectors have the same magnitude, the same size, and direction. They don't necessarily have to be laid on top of one another. Just as we saw here, we can have vector A and vector B as best I can draw it. Same length, same direction, right? They're parallel to each other. Okay. These can be the same vector. Numerically, when we start to calculate and manage with these, we'll see the values being the same. Okay. And so in that case, when we kind of think about that same direction, we might think that they kind of run parallel to each other. They don't necessarily have to be along the same line. That might be a case. Or they can be parallel. But again, the same direction, the same slope. Okay. And so just kind of going through, again, some of these little tedious components of introducing vectors, right? And so when we add vectors, right, going through some of these operations, when we add vectors, we add, all right, we kind of draw them head to tail, right? So if I start off with these two vectors, right? Definitely not having the same magnitude, the same size, the same direction. We have these two vectors. If I wanted to add vector A plus vector B, doing that addition visually, right? Tail to head, the head being the arrow, tail to head, okay? We start off, here's vector A. My best to kind of replicate up here. I might be a little bit shallower angle. But then taking the bottom, the tail of vector B, trying to maintain that size direction. There's adding those two together. And so the resultant vector, the sum of these two, my solution from head, or probably from tail to head here, working on the tail, head to tail there, right? There's my vector, my sum, giving us that final overall size and final direction of where I would be facing, pointing, if I was to combine those two size directions of my initial vectors, okay? And so there's my sum. We also can call this my resultant vector, right? The result of adding those two, okay? And so then here, a brief statement, a negative, or basically when we start to get into subtracting vectors as well, right? A negative of a vector, right? Like having negative A, okay? I know I've exaggerated that negative sign, right? Is that same vector facing the opposite direction. Right? This one's basically where it's going along that same line, but just flipping it over, going that opposite direction. So in that case, if we had, for instance, vector A here, a negative of that, whether you want to kind of just imagine it on this other side, would be like so. Or likewise, it doesn't have to be. That vector can live anywhere. Basically, all we're doing is kind of swapping, changing the head and tail. Okay? So same length, but just opposite in direction. As that comes in, if we're subtracting A minus B, the same thing as A plus a negative B, we'd be going downwards instead. And we can see those components. Okay? And some of the properties that we'll address later as well when dealing with these adding or later subtracting, watching those expressions, right? Watching your signs, right? Adding vectors, I'll stick to this, is commutative. So whether I do A plus B or B plus A, whether I do this A direction first, then the B, or B first, then A, I'm still going to have that same final resultant vector, regardless of which I do first or second. We just have to watch those signs, and when those subtraction or negatives come in, how those manage. Okay? And then another quick statement here. Scalar multiplication on a vector, right? So if we have some constant, some number, some scalar, right? No little arrow, that we're going to multiply times a vector. So there's my scalar, my constant, times my vector. What this does, this kind of either stretches or compresses that length, that magnitude of the vector, right? So for those scalars, those constants C that are bigger than 1, right, is stretching out, making that vector longer. For values for that scalar less than 1, some fraction, some decimal, right, it's going to compress it down. It's going to shrink it. If it's negative, right, it flips direction and also stretches, compresses, whatever that needs to do, right? And so, like we mentioned, if that vector A looks like so, if we had twice that, 2A, then it's going to take that original vector A, the direction is staying the same, but now we're going to actually elongate, we're going to stretch, right, double that length. Okay? So there's our scalar multiplication. We can work on those. All right. And again, some of these might be fairly simple to follow, to grasp, or you might need to look at this a little bit more. Okay. And so kind of going back to our notation discussion. All right. When we talked about before how a vector can just be this item, this object, I should say, connecting our 2 points, if you will, pointing from one point to the next, I guess more formally. We can have that vector A like so, right? Well, if we start to get a little bit more in depth here, this could be the point x1, y1, x2, y2. So that vector A can be represented as this notation here. We can use these angled, those bent brackets. And now, again, staying x coordinate, y coordinate to find how far we're going, right? That direction, that distance, how far we're going in the x direction, x2 minus x1. And then for our second coordinate, our second component, how far we're going in the y direction, y2 minus y1. And of course, in 3 dimensions, right, this is R2. In R3, we can imagine that a vector A would have 3 components. The difference in the x coordinates, the difference in the y coordinates, and lastly, the distance, the difference in the z coordinates. Okay? And so we can start to use that when we do start to see vectors in coordinate systems, whether we're starting at the origin or some other point, we can start to look at this representation. Okay? So, for instance, here, an example, right? Find the vector with initial point, (1, -2, 4, and terminal point, (3, 3, 6). Okay, so we can imagine this point. I know it might take a little more to plot in 3 dimensions, but our x, y, and z coordinate, terminal point x, y, and z coordinate. So having these 2 points in space and then trying to find that vector that's going to point us in that particular direction where that might be. Okay? And so again, I'm not going to do a spectacular job in graphing these by any means, okay? But just trying to get a glimpse at this work, at this idea, we have, I'll do it in blue back here, y is -2, so we're over here, x is positive, z is up here. So let's say this is our first point, 1, -2, 4. Then our last point, x is 3, y is 3, z is 6 up here. And again, I know it's kind of awkward to visualize, but we're trying to imagine this vector in space here. What is that vector going to be equal to? How could we represent the components of that vector? Okay, that's going to point us in that direction to connect those points. Okay, and so for that vector v, what we had addressed before, right, that x2 minus x1, y2 minus y1, z2 minus z1. And so doing those calculations, if we label, here's my initial point, my starting point, x1, y1, z1. Here's my terminal point, x2, y2, z2. So if we start to plug in, again, that series of differences, how far do we need to go in each of those directions? X sub 2, 3 minus x sub 1, 1. Y sub 2, 3 minus y sub 1, -2. Watch those signs. Z sub 2, 6 minus z sub 1, 4. So lastly, 2, 3 minus -2. 3 plus 2 is 5. 6 minus 4, 2 again. So that would be our vector. And as I mentioned, right, kind of looking at the differences in those x, y, and z coordinates, kind of like our slope before. This is kind of telling us, okay, along this path, along this vector, I'm growing by 2 in the x direction, growing by 5, or going up by 5 in the y direction, going up by 2 in the z direction. So when we start to think about those, if we have a negative, right, we're going downwards in the y direction or whatever it might be, we can slowly but surely start to tie in those kind of physical identifications, feelings, if you will, with these vectors as well. Numerically, we would kind of go through that straight calculation. And again, if I was to multiply it, if I was to do 2 times that vector v, just distributing that scalar 2 through, we can do so and expand the length of the vector. We can do that work. So the last little bit of information I'll leave with dealing with these vectors, okay, is now, right, to find the magnitude, the length of that vector. Okay, to find that magnitude, that length, well, as we just kind of saw, that vector really is just a point or a pair of points that we're connecting, right, pointing towards. So if I want to find the length of that vector, is just basically finding the distance between those 2 points, right? So for our notation wise, what we'll see, finding the magnitude, you see either these absolute value bars. In some cases, you might see the double bars. Okay, either way, find the magnitude of that vector, just finding the difference, the distance, the length of those. And if we had our vector v, let me sneak down here, as these coordinates, and I think but we can do A, B, and C. Right? These were those differences between the terminal point and initial point, terminal point, initial point y. So those are those differences. We can just take those components and square them. Take the sum of those quantities squared, put on the square root, and there would be our magnitude, right? And it's just like the distance formula. We had already done those subtractions, right, in constructing that vector. And now we're just computing like so. Okay, and then one last component here, right? Vectors with magnitude 1, right? Magnitude or length 1, exactly 1, are called our unit vectors. And those are typically written with a little hat. Instead of the vector line, right? The little hat. Instead of the arrow, lets us know the magnitude is 1. All right, we can always compute, but there's just a little notation. And we'll see some use of those unit vectors as we go along as well. Okay. And so in the book, they have some different properties working with these vectors, computing, which we can address as we go along. Okay. But here's our introduction, some of the terminology, notation when dealing with these vectors. All right, so I'm going to stop sharing this. I'll post these notes as well as this recording for our Canvas site, so we'll have opportunities to review, ask questions as you see fit. All right, thank you very much for your time. I'll post some other video as well and also get into some problems to practice with. All right, take care.